Okay, welcome everyone. So in this session, we'll see all the weak fake concepts. Is my screen visible?
Yes, sir.
Yes. Okay. Okay, good. So this week 5 and 6 is very important as they play very important role in designing a database, and it involves lots of concepts also. Uh, I agree, like sometimes it's too tricky or it's not understandable at one shot. Okay. But I'll try to cover in a simpler way so that you will understand all those concepts. But still, you might have to rewatch once again, or you have to practice all those questions because this is very, very important in order to design a schema of the database. As we have seen, week 4 is also a part of designing the schema of database. We learned about ER diagrams, entity relationship diagram. So in this week 5 and 6, we'll see how can we design uh, good schema so that it doesn't have any duplicate values. What does mean by good design of schema? All those things we'll see in this week 5 and week 6. Okay. Okay, then fine. We'll start with redundancy. So I hope everyone knows what is mean by redundancy. Redundancy is nothing but it's having multiple copies of the same database, and it leads to anomalies. So while we storing some data in database, basically we are going to store it in the table. As it is a RDMS, we are following the RDMS one. So we're storing something like in a table. Okay. If I'm storing a course name without any course IDs or something, and if I'm storing something, same information again somewhere, if I'm updating the course here, I need to update here also. If I'm deleting here, I need to delete also. Like storing the redundant data from one same information in one table and another table also. It's not a ideal approach, or it's not even a good design, because maybe I'll tell at the last, maybe at week 6, after week 6, or at the end of the session. What it does is it reduces the, uh, it actually leads to anomalies. That's the problem of having redundant database, redundant data. And coming to anomalies is nothing but inconsistencies that can arise due to data changes in the databases with insertion, deletion, and update. Whenever we perform something, uh, like if you are gonna insert something in a table or delete something in a table or update, so there you may expect, not expect, that may rise to inconsistency. Basically, deleting some information will also delete the important information which is not supposed to be deleted. So that is called a deletion anomaly. Same for update anomaly. What is mean by update anomaly is if you are updating something, it's updating the other row which is not supposed to be updated. Similarly, for insertion which is not allowing to insert, or if you are inserting something, it modifies one or two information. So these three types of anomalies, those are in the databases. Uh, any doubts here? So that I'll move further. This is just an introduction before moving to the actual concepts.
Sir, can you explain update anomaly again?
Okay. I'll take an example, maybe short example. I'll take something student ID. student name, course ID, or let's say this name as course, let's name it as course, and the instructor name. Okay. Let's have student ID 1, 2, and name as some random name, which could be ABC, XYZ. And the courses, let's say DBMS, or MAD, or whatever subjects. And this is Professor uh, PhD, and this is Professor. I think, right? So, and if you wanted to change, let's say one more, this is MAD 1, and this is something JKL something student. They say this has MAD 2, and this is also Professor Nathan. Yeah. And if you want to change professor, instead of professor, let's change, if you want to change this to doctor. So you need to change it in multiple rows, right?
Yes.
But that shouldn't happen. If you are changing one's name somewhere, it should reflect everywhere, right? That should be the ideal scenario whenever, if you are using any application, right? If we change somewhere at once, it should reflect everywhere to your in the application at least. So if we are storing the information in this way, you need to update in the every row repeatedly. So this causes update on inconsistency. If you are forget to update the second row, in one place it will show Professor Nathan, in another place it will show Dr. Nathan. Right?
Okay.
This is called update anomaly. In similar cases, you can check for insertion and deletion also. I hope now you are able to understand what is meant by anomaly, everyone.
Got it, sir. Yeah.
Okay. Let's move to the next one. This is again just give to an introduction. Why we are studying all these concepts in week 5 and 6. So basically, what it does is storing redundant information causes anomaly, and this dependency causes redundancy. I'm just coming in a reverse way. And this good decomposition, if there is no good decomposition, it should cause to minimization of dependency, and normalization should cause to good decomposition. So basically, what you wanted to do is you need to normalize your database. So which we will study in week 6. How to normalize the design which we have designed, so that is it normalized or not, so that will remove redundancies and anomalies, because everything is interlinked, right? So if you are having a good normalization, that will lead to good decomposition, and if you are having good decomposition, and that will lead to minimization of dependency, and if we are having good dependency, it won't have redundancies, and redundancies will remove anomalies. That's the whole concept of week 5 and 6. As of now, it's very difficult to understand. I agree. But maybe after week 5 and 6, once again you come and revise, then it will be very helpful to design a database, so that how we should design a database. At least you should know all these principles while designing the database, so that your database design will be optimal, so that you won't store redundancies, how to store the data, all those things
Excuse me,
will,
sir.
at
Excuse
least you
me,
will
sir.
be aware. Hmm.
Excuse me, sir. A small
Yeah.
question: is this notes which you are teaching from would be available somewhere? I am not getting.
Uh, yeah, I shared in the last session also.
Okay, but where it is? Please.
I have shared a drive link. I will share it now also. Just um, I have pasted the link in the chat. So I haven't uploaded this week file. We'll update it after the session. Okay. So let's move to the concepts, and so we'll come in a reverse way, like we see dependencies in this week 5, and before coming to decomposition and normalization, we'll see what are the other concepts that is involved to check all this has been properly designed or not, so that we can verify all this has been uh, passing or verifies our checklist, because it has some rules. So we'll see all those things in upcoming steps. Okay. So functional dependency. And what is mean by functional dependencies is it's a relationship between two set of attributes. It's not two attributes, it's a two set of attributes. So what does mean by attributes? Can anyone?
Two columns like
column names.
So we can say all the columns A, B, C, D, all those is attributes. So you are gonna define a relationship between two set of attributes. That means it has, you can take two columns as a one set of attributes, or three columns as a one set of attribute, and next two column 2, 3, 1, any columns as a another set of attribute, and you are gonna define a relationship between. And let's consider this alpha to be the subset of a relation and beta to be the subset of relation. And if a functional dependency alpha to beta holds on relation R, if and only if this condition should be satisfied. So how many of you are agreeing this is not clear by looking at the statement or whatever I'm saying?
It's not
Yes,
clear.
it's not clear. It's not clear.
Okay. Because when we also started it, we felt like that. So okay, let's see with an example, like in a simple manner, uh, how it's defining the functional dependency. So this is A and this is B. This is nothing but two set of attributes, right? This is one set of attribute, this is one set of attribute. And here we are considering two attributes as a one set of attributes, and this is one set of attribute. In other cases, we are considering this as a one set of attribute, which has two attributes, and this as a one set of attributes. Now, I hope everyone is clear what is mean by attribute and how we are defining this relationship. Basically, this says the student, how we used to say is this arrow symbol. This determines the student ID determines semester. So at least half of the things were clear, right? In functional dependency, what is mean by attribute and how we are defining this one. So let's see how the student ID determines semester. We'll see in using this example. Any doubts so far? Okay. So taking this, how to check whether this dependency is true or false? How can I check this is true or false?
If we change the student ID, semester should also change.
Not I'll say an easy way. This is student ID, this is semester. First, let's take the left side, which is student ID. This 1234, 1221, 1201, 1234, 1234. First, let's check. You need to check whether the left side values are unique in that attribute or not. If it is unique, you can straight away say this is determining the other attribute. If it is unique. For example, I'll take another example using the same column here only. If say student ID 1, 2, 3, 4, 5 and semester 6, 4, 2, again 2, 3. Here the left side, again I'm taking the same one only, student ID determines semester. Here the left side is all unique, right?
Yes, sir.
All the rows were unique. So in this case, I don't even need to check this right hand side, whatever the values it's holding. I can straight away say this student ID determines semester.
Sir, but if it
Clear?
is not unique, we cannot confirm or deny.
So I'm coming to the first case. I will explain the second case also.
Sorry, sir.
Okay. This is clear.
Yes, sir.
Okay. In second case, what we are checking is in this example, as I have given here, it contains duplicate values, right? In student IDs. Here 1, 2, 3, 4 is there. Again, here 1, 2, 3, 4 is there, and this is not found in a second time, and this is also found second time 1, 2, 0, 1 and 1, 2, 0. In this case, if it contains same value again in the attribute which is present in left side, so then how can we proceed? Right? The simple thing is, if 1, 2, 3, 4 determines 6, here it's determining 6. Here also this 1, 2, 3, 4, wherever the same value appears second time, that should also determine the same value which has been previously determined. If it is determining here 6, it should determine 6 here. Then only this functional dependency satisfies. If it's not 6, if it's 5, 3 or some other value, then this dependency is false. This dependency is not true.
Yes, sir.
Sir,
What?
one thing, can you just put it into words? I understood the logic, but I'll forget it sometime. Just make it into a sentence. I can't think of it.
Maybe he'll try to add it in the slide later. Uh, Is it clear or not? Should I? First thing is left side value should be unique, right? This is first condition. If it's not satisfying, go and check. Two same values or two or more, anything it could be. Two values on the left side should determine the same value
On the right side.
or a similar value. Similar value on right side. So, any doubts in functional dependency? I hope I explained in simpler manner as I can.
Yeah, no, sir. Clear, sir. This is like we read function in 12th.
Okay. And when considering the second one, I'll take second one. You just consider third one by yourself. Okay. And considering two attributes as a one set, what you have to do is you have to consider these together as a one value while determining some other thing. Considering 1, 2, 3, 4, 6 determines John. Sorry, it's not semester.
Lecture.
Lecture. This 1, 2, 3, 4 numerical methods determines John. Here, let's see 1, 2, 3, 4 visual computing determines Bob. Right? Here also two values are same. But when you combine with two attributes, you need to check as a single value. 1, 2, 3, 4 numerical methods is different. 1, 2, 3, 4 visual computing is different. So you should consider this as a unique. So if
Yes,
it is
sir.
unique, so you don't have any problem with right shift, right?
Yes, sir.
And if you check for others also, you doesn't have any problem that it determines this and that. Okay. So let's move to next concept.
Sir, what if there is duplicate when we take the two attribute in a set?
Okay. For example, here, if it has a duplicate value here, numerical methods, this is duplicate, right? 1, 2, 3, 4, 1, 2, 3, 4. And here also, if it is numerical methods, then it's duplicate. Then in this case, is it determining so far? Like here it is Bob, here it is John. Is it determining whatever the relation it's given here?
No, sir.
Anyone? No, right? So if it should determine, this should also be John.
John.
Same rule should consider 2 or 3 attributes as a single one. If it is 2 attributes are there present in left side. That's why in definition it's given as a 2 set of attributes to determine the functional dependency. Okay.
Sir, just
Sir,
wanted to confirm the
Hmm.
first statement that you wrote on the top right, that is,
Hmm.
if that statement is satisfied, we don't need to check any further. But if it
Huh.
is not satisfied, we have to go to number 2 statement.
Yes.
Just wanted to confirm. Thank you, sir.
Yeah. Okay. Then we'll go for the next one. This is trivial dependency. It's as simple as that. It's nothing to complicate. A functional dependency is trivial. Let's say this student ID determines semester satisfies trivial if alpha determines beta is nothing but left side of attribute, left set of attributes and right set of attributes.
Sorry to
If
interrupt.
b
Sorry to
if
interrupt.
beta if beta is a subset of either it could be proper subset or same attribute, then it is trivial. So for example, if student ID determines student ID, this is trivial. This will be true for every set of attributes wherever you take, because it's both are identical. Even though they may not say explicitly in the table or wherever in the question paper, it's always true. A same attribute can determine by itself. This is true. And this is trivial also. Okay.
Sir, beta is a proper subset of alpha, right?
This is not
Yes.
proper subset. If underline is there, this is not proper subset.
Okay.
And if semester is there, let's say this two attributes determines together semester again. This is a proper subset, because here semester is a proper subset of the student and semester, and this is also trivial.
Yes, sir.
And this I have given in other examples. That's it. Okay.
Excuse me, sir, just go to the previous slide, previous to this one. Yes, the last example. Student ID, lecture to TA and semester. Could you just explain again? I was writing down the second one when you completed the third one. Just once.
If I'm not getting what should I explain here?
Student ID lecture to TA and semester. How you explained it? Yeah. Last line.
Okay. You can rewatch again, because why I am going in little fast is
Hmm.
only this session is there to cover all the week 3 concepts. Next session will be week 6. That's why.
Okay.
So I hope it's clear on the first time, so you can rewatch later also.
Okay. Thank you.
Okay, that's fine.
Sir, one question. So you pasted the link actually of the drive. So I can't able to. It's a text actually. It's not a link. So I can't able to copy it.
This slide is not uploaded.
No, the drive link I'm saying, sir. You pasted in the text, no?
Hmm.
So it's as a text. It is not as a link. So I can't able to copy it.
I don't know why this issue causes.
Yeah, everything. Maybe it's for me. I don't know, sir. Could you
It is
please share?
copying.
Is it working?
Yes, sir, it is
For
copying.
me as well.
Is it accessible to all?
Yes, sir.
Yes, sir. Sir. Could you paste it in the calendar, sir, if possible?
Okay.
Sir, if we bookmark it, will it be available later after the class?
Hey, are you guys seeing the slides or like I shared what something else?
No, sir, you share the slide. It is showing what the link of your drive sharing is also be there in the chat box. Someone has problem on there. So, sir, continue, please, sir, continue.
Just wait a moment. Just a minute, I'll be back. Am I audible? Sorry. Mm. Hello.
Yes, sir. Now you are audible.
Yes, sir, audible.
Earlier you weren't, and mics were muted too. I guess.
Okay. So I pasted the link again. Okay. Sorry. That was the wrong link. Is this slides are visible in this link? Using this link?
Oh, yes, sir. It's available there. Thank you.
Okay, then let's continue. Um,
Yes, sir.
okay. Then let's come to the some of the Armstrong axioms. Then what is mean by reflexivity, augmentation, transitivity? Uh, I don't have anything to say. You just need to remember these rules. If beta is a subset of alpha, then it is alpha determines beta. And augmentation is nothing but you are adding an extra attribute here on the both side. That is called augmentation. So you have seen I have added gamma on both sides. That is augmentation. And transitivity, in simple words, how can I say is if A determines B, if B also determines C, I can say this A determines C. This is called transitivity. And union, again, just combine them and together you can write it. If if A determines B, again if A determines C also, you can write A determines BC like this. And decomposition in the same way, you just split it up and write it. If A determines BC, you can write A determines B and A determines C.
So what does BC mean? Beta gamma over here. What does it mean?
It's
Like,
just a attribute name. Instead of
so
saying full attribute name, student ID, student name, in simple form, I just given as a formula like.
I got alpha and beta respectively, but what is the meaning of joining these two, like beta gamma?
You are adding one more attribute which is present in the table. If you are adding that attribute, that condition is also satisfied. That's it.
So my understanding is if alpha is dependent on if alpha determines beta and alpha determines gamma, then alpha
Mm.
determines both beta and gamma. Is that what you're trying to say? Or
Yeah.
what is meaning of this alpha determines beta and gamma like together? What does that mean? That is my
Which property you are talking about? This
union.
union, transition, union.
Yes.
So in this case, it's nothing but if A determines B, are just replacing it. Okay. If A determines C, if I can say this two are true, I can say this is also true. A determines BC.
Okay, so you're defining it as if this holds and if this holds, then this will hold.
Yeah.
Okay, and sir, could you please explain augmentation as well again? If alpha determines
Augmentation, it's nothing but you are trying to add one attribute. If A determines B, then I can say if I'm adding any attribute, I will put something called X. Then this is also true. I can, if I am adding both side same value, right?
sir, I think I understood. So it's like if beta is student and gamma is course ID, it's student and course ID, comma. It's like these two attributes we're talking about. Am I
Hmm.
right, sir? Yeah.
Yeah,
Got
yeah.
it. Yeah.
Okay. Shall we go to the next slide then?
Yes, sir.
Okay. Okay. Let's move to the next one. Closure of attribute set. This is very, very important. How to find a closure of any attribute set? Because everything is dependent on this only, all the coming concepts. Okay. And if you want to find closure for any set, because something you might have seen in activity questions or practice assignment, something like this will be given. Because instead of writing as a full name, I am just denoting as ABC. In following also, I'll do the same in upcoming slides also. Okay. These are all attributes, and this is function dependencies were holding true. And if you wanted to find a closure of any set, for example, AC, what you need to do is AC closure. And this A determines B, right? So what I can put A, C, B because it determines. Again, how can I proceed further? Again, you can take a closure of this and you can see this BC determines GI. So I can write like this ACBGI. Again, you can see G determines CS. C is already there. So what I will do ACBGIH.
Sir, here, what do you mean by R and in brackets ABCGHI is R is a relation, right?
Yeah, relation with the following attributes.
With the following attributes. Uh, what is the plus mean? I didn't understand.
Plus means this closure. What is nothing but closure. This plus denotes a closure of it. If I say what is the closure of BC, what will be the closure of it?
First B and C.
GI.
GI.
With B, C, G, I, then after that nothing is there.
Yeah, BC, GI will be there. Then H will be there since C is already there. But A can't be there, right? Because you are not getting A from any of this.
How H is there?
GCH.
Oh, acha. Very complicated.
Okay, right.
Sir, what is this? Could you? I'm sorry if I'm slowing down the class, but I couldn't understand. FD, FD is equal to A dependent on B. What does this FD mean?
FD means is a short form of functional dependence. This relation is having all these dependencies.
Okay.
So what we
Oh,
call is functional dependency set for this relation. That's
got it. Got it.
okay. So what we are typically meaning relationship is nothing but it's a table. This table has these many columns or attributes, and in this all these dependencies were there. So we are calling as a functional dependency set. So that's why it's written using set notation.
Got it, sir. And sir,
Okay.
AC plus is equal to AC means that
Close, you are taking a closure for those attributes, and closure nothing but what closure says is if I'm taking AC closure and it's giving A C D G I H. Using this, what I can say is this AC determines all these attributes. That's what typically we are coming to say. Okay.
so is it A and C, both A and C, not only A, not only C, right? I just wanted to clarify.
Yeah, both.
Both A
because
and
we are
C.
taking closure for both, not individual.
So instead of writing this plus sign and equal, if we just write dependency, isn't it the
Hmm.
same thing?
Can you repeat again?
We are writing this arrow for is dependent, right? So
Hmm.
what is the difference between this closure and this arrow?
No, it's another way of checking whether these dependencies are linked or not. See here, A is not linked to G or C, something like this. Okay.
Right.
And again, if you take this AB, it's not linked to somewhere here. So that you can check if you are taking closure of this, it's determining that or not. So using that, there are other concepts of candidate key and super key also, which we'll see in next slide.
Got it, sir. So, sir, here we are saying that so AC plus means what and all are functionally dependent on A and C both.
Hmm.
Okay, and every subset of AC, B, G, I, H is a part of AC plus. Is that a
Hmm.
correct statement?
Yes, yes.
Got it, sir. Thank you.
Next, we'll see what is mean by candidate key. Candidate key is nothing but set of minimal attributes that uniquely identifies a tuple or row.
So how is it different from a primary key? Just asking.
Okay. So far we have studied primary key and foreign keys, right? I hope everyone is aware what is mean by primary key, right?
Yes.
Yes, sir.
So, in fact, in simple words, how should I say is primary key is one of the candidate key. This primary key is one of the candidate key.
Which is unique and not many.
Huh. Because candidate key also its definition wise same. Okay, a set of minimal attributes that uniquely identifies a row. A primary key also does that. A primary key identifies a row uniquely. So
But
it's
candidate
nothing but
key,
one of the candidate.
can candidate key be null?
No. I said it's one of the primary key, right? How it can be?
So, sir, it is like primary key only.
So it's like we are picking the primary key from one of the candidate.
Okay, so all those attributes which satisfies the qualities of a primary key are called candidate key.
You can choose any one of it to be a primary key. Actually it depends upon the design and the requirements of the application, so that you can choose any one of it. It doesn't have any specific rule, so that you have to pick this candidate key as a primary key.
Yeah, right, sir.
Okay. And superset type. Superset of any candidate key is super key. So how I can represent this? A candidate key as a subset or equivalent to super key. This is how I can symbolically represent candidate key. And it's nothing but you are adding extra keys in a candidate key. If I say AB is a candidate key, I can say AB G as a super key. It could be any other attribute. Got it?
So, what is the use of super key?
Because in week 6, it has some conditions to check the normalizations which we have discussed, so that you have to know what is mean by super key.
So in the set of candidate key, we can add any of the attributes to
Yeah.
make a super key.
So that is. So also one more thing is every candidate key is also a super key, as you mentioned. You have to take care of all these notes wherever I have given. Okay.
Do you have any real example like student table?
We'll see some upcoming examples. I have examples also. Okay.
Okay.
So this is present in candidate key prime attribute. Every candidate key is super. Next, there will be some questions you might expect. And there are some questions in activity and practice assignment also, I guess. And as of now, I'm just giving the formulas to you. Formulas to find the maximum number of super keys. So this n is the attribute. So it can be 1, 2, 3, 4, 5. This n denotes the attribute. If there is only one candidate key, that means single attribute. You can use this formula to find the super keys. And if there are n attributes, one candidate key is found by using two attributes like this. You can use this. This k is nothing but how many attributes are present in candidate key. And if each attribute is a candidate key, you can use this formula. And if two different candidate keys formed by one or many attribute, you can use this one. So I just don't want to read the formulas again. So we'll see one example, but do remember all this. So in this example, this is the relation and these are all the attributes. Okay. And this is one of the candidate key and this is one of the candidate key. Okay. The question is, what is the maximum number of possible super keys of student info? So we are using it. So first we'll find the super keys for the A attribute. This one, let's say this alpha, beta. Okay, this one, and let's find the super keys for this one. And let's find the subtract the super keys, whatever found as common between them. It's almost like set formula, right? The set formula which we have seen in basic mathematics, n of a union b is equal to n of a. There's n of b. We subtract whatever it's found common in both this. We'll just subtract it. In the same way, we are just subtracting the number of super keys which will be common to both of this. So that's why it's m plus n here. So here, the why we are 5 is there are total number of 5 attributes. Okay. In the case 1 m, here this will be the m because the candidate key is formed by only one attribute. So that's why it's 1. And here again this is m, total 5 attributes. Here the candidate key is found by 3 attributes. So it is 3. And here it is 1 plus 3, 4, 4, 5 minus 4. Because together if you take, it's 1 plus 4. Sorry, 1 plus 3, it's 4. Then you will be coming up with this. And if you simplify, that is 8.
Sir, I am not getting it. Can you repeat how this 3 and 4 came?
Where? Here.
What do you mean by the max number of super keys?
Sir, can I?
How we calculate this one? The maximum number of super keys.
So you're calculating using the formulas, whatever we have seen above, right?
Yeah, basically, how you define aid and aim?
How we?
small m and n.
Number of attributes.
Okay, how we are defining this m and n, small m and n? This m and n comes from here. This is my candidate key 1, this is my candidate key 2. And this candidate key, only one attribute is there, right? Only enrollment number. But in
So,
this
sir,
candidate key,
candidate
there
key
are 3
2.
attributes. No,
Yes, sir.
3
Sir, in
attributes
candidate
were there.
Class,
Okay,
sex, or
so
roll.
in one
That's why
candidate
this is
key,
3.
sir, in one candidate key, can we have 3 attributes?
Yeah.
It is set of, okay, it is a set. Candidate key is a set. Huh?
Yeah.
It is a minimal set, like.
Okay, this is not a single attribute.
Yes. It can be both, na. Single.
But primary key can be 2 or 3 attributes also. Generally, whatever we have seen in week 2 and week 3, it's considered as, we have considered this as only one attribute as a primary key. So, but candidate key is something, it can be 2 attributes, 3 attributes, but it should be minimal. That's it.
Sir, it is a minimal super key, na.
Yeah, you can rephrase it like that, because every candidate key is a super key.
Yes, sir, got it.
So I just skipped this formula alone, read it once again. And if you guys have any doubts here, maybe I'll explain it, or else we'll move to the next question, because this is very important, whatever the concepts I'm going to discuss next.
Sir, can you repeat that M and N part? How we calculated M and N?
M and N is simple, right? Whatever the candidate key you have, how many attributes are there, that depends on M and N. In this case, this is M, because M is equal to 1 because this has 1 attribute. In this case here, N is equal to 3 because this candidate key has 3 attributes.
Sir, could you show that slide, the previous slide? I just wanted to read it once.
This one?
Yeah, yes, sir. Got it, sir.
And now let's come to the concept of extraneous attribute. Here, whenever you define some dependencies, it could be like this, it could be like this, whatever, right? In sometimes what is happen is this might be unnecessary, so that we don't even need to include in this dependency. So, and this is called extraneous attribute. And how can we find this extraneous attribute and how can we remove them? Are you guys getting my point?
Sir, it's redundant.
No, sir. I'm not getting.
Okay. We used to define dependencies, right? Something like this. As we have seen in the first slide, we have defined a dependency between student ID, lecture, TA's courses, right? So, assuming that this dependency you found from the table, and some dependency, sometimes that could be not relevant to you to define this, because this could be unnecessary or redundant, that we are calling as extraneous attribute. If we can remove it without changing the closure of the set of functional dependencies. Okay. So we are calling this as redundant. Similarly, left side also it could be redundant. So we'll see how to find this extraneous attribute. We won't call it redundant. How to find this extraneous attribute So how can we remove them and how can we rewrite this dependencies? Okay. So there are two cases basically here. So which I hope by looking at this it won't be clear, right?
Sir,
So
is this this content is there in week 5? I have not read it in week 5. This is week 6 or week 5?
week 5.
Extraneous attribute, I don't think this content was there.
So this is there. This is the actual two points to find the extraneous attribute. So I'll go with an example instead of explaining this definition, because by looking at it, I hope everyone feels this is something written as a equation, right? Okay. So this is for the first condition, whatever I say here. This first condition is nothing but to find the
Sir, please
extraneous
stay on
attributes
this slide.
left side. The second condition is nothing but to find the extraneous attribute on the right side. Okay.
Sir, just
So
want
we'll look for the
confirm, sir. When we say alpha is dependent on beta, which one is the one that is uh, creating the dependency? Left one or right one? Alpha is dependent on beta.
left one.
So left one is dependent on the right one. Just wanted to confirm.
Dependent or determines?
Dependent.
It should determines.
So
This
alpha
beta is dependent on alpha.
Ah,
If I say in this way, this is dependent. If you say this one, this is determines.
got it, sir. So the arrow means determines and the other way around is dependent. Got it, sir.
That's it. So let's look for the first condition. First condition is nothing but to find an extraneous attribute on the left side. So in this case, we are having two attributes here. So any one of it could may be extraneous. We cannot say that is surely extraneous or not surely extraneous. It could be extraneous. In order to find this, what we need to do is you need to take a another set of functional dependency by removing B. Why we are removing B is because we are checking whether B is an extraneous attribute. Whatever the attributes you are gonna check, you remove it and rewrite the functional dependency, right? Because I'm gonna check for the extraneous attribute B. So I'm just removing it, this B from here, because this B only I'm checking, not the B in whole functional dependency set. Okay. So I'm just removing that and rewriting it as F dash. So if I want to write as per the condition, this will be like this. You might just subtract it and write it. Now you take a closure of this after removing, because here you removed, you take a closure of this A closure. And after taking the closure, you will get ABC, right? Because if you take A closure, this A determines B, and this again A also determines C. Once you've taken a closure and you got the attributes right side, whatever it's there. So if you are finding it B here, after removing and taking the closure, if you are getting the B attribute again, then it is extraneous attribute. Is it clear?
No, sir, please repeat. I am getting confused.
Sir, as far as I'm understanding, if like a B attribute is unwanted here, without B, we can also closure of A, we can get every attribute, right?
Hmm.
So B is unwanted. If we remove B, then nothing is gonna affect on our attributes or closure.
Yeah.
Okay.
Should we move to next
Sir, I am also not getting this.
Same, sir. I couldn't understand.
one? Everyone is clear about this closure, right? At least.
Yes, sir.
Yes.
Yes, sir.
Just be clear with it. In this left side, what I'm gonna check is I'm gonna check whether this B is extraneous or not. In order to do this, what I will do, I will rewrite this functional dependency as f dash by removing that B. I just removed it. Okay, this is clear.
Yes.
So what I will do, as I removed B here, I will take a closure for this A where I removed it. Because here I removed B and here I will take closure, but I will take closure in this f dash only, not f. Okay. If I take closure, I will get A, B, C. After taking the closure, if I get the attribute B after removing it, so because I removed it in f dash, but after getting the closure, if you got a same attribute, then it is extraneous attribute.
But in the just below line, we are subtracting it from AB and subtracting B from AB, then finding the closure of A.
Huh.
We can directly do the closure and check rather than doing this the last step.
Yeah, that also for this one. Okay.
Yeah.
So
So
for
this is
second
for
condition,
left side checking.
yes. For right side also, you just do, if you wanted to check some as a extraneous attribute, you can just remove it and rewrite this as a functional dependency. So in this case, what we are doing, we are just taking the C as a extraneous attribute. I just removed it and rewritten it. And you have to take the closure of left side. Always you have to take a closure of left side. And if you take a AB closure, we'll get ABCD on this dependency. And again, you got a C after removing it, right? So if you are getting something after the closure on this f dash, that is called extraneous attribute.
Got it.
So the second condition is also clear, right? Basically, what we need to do is we need to remove it and rewrite the functional dependency as f dash. And you take a closure, whatever it's there on left side. And if you are getting the removed attribute again in the closure, then it is called extraneous attribute. If you are not getting it, then it is not.
So how do we calculate the closure, sir?
Just a minute.
Sir, you are not audible.
Excuse me, is the chat disabled for everyone or just me?
No, Sir is not audible.
You're not, sir is not audible. Yes.
But
Or sir is even teaching or what?
because the cursor is moving, that's why I doubt.
Sorry, I got a call. So this is clear, right?
Yes, any one of the condition must satisfy for an attribute to be called as extraneous, isn't it? Okay.
So every time we have to check with the left side and right side both for B and C and whatever is there.
Sir, you are not audible.
I'm audible now. Sorry.
Yes.
Now you are audible, sir.
Okay, let's move to next one. I hope it's clear. And the next concept is canonical cover. Okay. The canonical cover is nothing but you need to minimize the dependency again using all the concepts that we have studied so far. Okay. And minimizing the dependencies, like some functional dependencies that will be there. You can minimize by removing the extraneous attribute and the redundant functional dependencies by using Armstrong axioms. And you can write all the single attributes on the right side. This is the steps you can see. So we'll see that this is also with the example. So that it covers all these three. You need to follow all these three to come with a canonical cover. This functional dependency is nothing but A determines BC, and A also determines B, and B determines C. So what happens is here A determines BC, A determines B, and B determines C. All these things were there. Some of them could be redundant dependency, so that we can minimize this dependency. We can write it in a simpler form like this. So this A determines BC, I can write it as A determines B and A determines C, right?
Yes.
So this will be now, it will be like this if I split it and write. So I can remove one of it because since it's duplicate, right? And now this A determines B and B determines C. I can remove this A determines C also, right? I remove
Yes.
this.
And AB determines C also.
Because this is a property of transitivity. Right? And you can, if you check this is also again, you can check for a redundant attribute on the left side, and if you remove one of it, and it will be again duplicate of something like this, or you will get a transitive property, you can remove this also. So I'm not doing extraneous attribute again. So by checking for redundancy and extraneous attribute, if you split it and write, you'll get a canonical cover of minimum, this A to B, A determines B and B determines C. Right?
Yes.
Yes, sir.
Okay. Shall we move to the next concept?
Yes, sir.
I'll upload this slide in this drive link. I pasted and pinned also. So next we'll come to the concept of functional dependencies, basically equivalence of functional dependencies. And there is something called whether this dependency set covers that dependency also. So that is called equivalent of functional dependency. If F covers G, how can I say means this is nothing but a functional dependency set. This is one set, this is another set. So that in simpler word, this F should be a superset of this one, superset or equivalent, so that all the relations should satisfy on G while taking the closure of F. If I take closure of F, all the condition on G should satisfy, so that I can say F covers G. So I can symbolically represent in this way. And G covers F. This F is a subset of G. Whatever comes left side, that can be a superset, and whatever comes right side, it should be subset. Not in terms of functional dependency set, in terms of the dependency conditions that it satisfies, so that it determines indirectly also if you take a closure. That is what it's mean by, okay. And all relations will satisfy on F while taking the closure of G. If both conditions satisfies, we can say F is equivalent.
Hello. Sir, what is the difference between F and F plus and G and G plus?
Functional dependency set. It is.
No, what is the difference between F and F plus?
F plus is a closure when you take a closure of some attributes, right? Generally, what we used to do, we used to take some candidate key and we used to take closure. In order to find candidate key, we used to take closure something like this: AB plus A plus. So this F is nothing determines the functional dependency closure. Generally, this is what symbolically it denotes, but I'll give you an example in next one. Okay, here. So this is my F1 or FG, whatever you say. And this F satisfies P and Q, Q determines R determines P. And this P determines R, and Q also determines R, and R determines Q. Well, these are the dependencies that present in the dependency set. So if you want to check F1 covers F2, so I can symbolically represent this as a F1 closure as like this, as a definition. Okay. So in order to check this, actually it's F1 covers F2 or not, what you do is you take a closure of F1. As I symbolically denoted, I'm taking the closure of F1 on all the left side attributes. So I take closure on P, it gives PQR on the F1. Okay, I'm taking on F1. And again, I'm taking on closure of Q and it gives QRT. Again, it gives all the attributes. Again, if I'm taking R closure, it gives all the attributes on F1. Clear so far? Hello.
Yes, sir. Yes.
So while we are taking the closure of all attributes, can't we check by taking the closure of only P or Q or R?
This is easy way, but you can do in that way also. Okay. So I'm just taking it. I'm not checking whether this is covering F2 or not. As of now, what I did is, this is the condition. I have taken F1 closure, and these are all the closure values you got. Now let's check whether this covers F2 or not. This is a simple way to check in an easier way. Okay. I think so far it's clear, right?
Yes, sir.
This P closure, it's nothing but now you have to check whether all these dependencies are satisfying in my F1 or not. Satisfies in my F1 or not. Right? So how can I check this? To take this dependency, how can I check this dependency satisfies in this dependency, as there is no direct dependencies like that, right? So what I will do, I'll go and check for this closure one, because it's P, so I'll take check in the closure one. So by taking P closure, I got R. So if this is true, I can say P determines R. So this is satisfied in this F1. I hope now you will be able to get why we are taking closure and how it's linked to the dependencies. If you are getting some attributes by taking the closure of it, then you can say closure of that attribute determines whatever present on the right side.
Sir, one small question. Here P plus is written as PQR because from P it implies Q and Q implies R. But yeah, if I write RPQ, it is here it holds because of taking closure. But in generally, if I write in different orders, will it hold true or false?
Different orders in the sense, like
Instead of P plus, here P plus is equal to Q plus is equal to R plus. Instead of P plus is equal to PRQ, I write it as QPR.
yeah. Order doesn't matter on the right side.
Okay. For even when they are not, when there is, the full closure will be held, right?
Yeah. This closure I can write PRQ. This closure also I can write PRQ. This closure also I can write PRQ.
Yeah, that's
Order doesn't matter. Okay. So this is satisfied. I will erase some of this also. This is satisfies. Now let's check for this Q determines R. Let's check Q closure and whether this Q closure has R or not. So that it has R. So we'll check this Q determines R. This also done. Now check for RQ. Check for R closure and whether R has Q or not. It has. So it has Q also, and this is also true. If all the dependencies were covered in F1, we can say F1 covers F2. Because taking the closure on F1, all the relations satisfies on it. Is it clear? So that this is true. So I'll give another example also where it's not true. Sorry.
Sir, could you please go to previous slide?
Yeah.
From where we are getting P plus is equal to PQR and Q plus is equal to Q.
By taking closure on this type.
Sir, how do we derive the closure?
If you take P closure, this P determines Q, right? So I can write PQ. Again, Q determines R, so I can write, because Q is there. So what I will do, I'll take PQ closure. This Q determines R. Again, I'll take PQR, right? Since R determines P, again, P is already there. So maybe
So
there is one
does
tutorial.
sequence matters here?
Yeah, sequence
See,
doesn't matter.
so here in the letter you have written P plus is equal to PQR and Q plus is equal to QRP. So both are same.
Yes, same.
So we can say P plus or Q plus is equal to Q plus or is equal to R plus.
Here it is true, okay? Because everything has the same attributes on the right side.
And
so
P plus is equal to PQR means P can determine the values of P, Q, and R, all three.
Yeah. So this P can determine Q also, P can determine QR also, and all three also.
And in this case, sir, we can write P plus is equal to PQ plus also. Okay.
So let's look at next condition similarly. It's same question, but we are gonna check in reverse way whether F2 covers F1 or not. So symbolically, how can I represent? We'll take closure on F2, and this should be a subset of, right? Whatever is coming right left side, you can take closure for this. You take closure on F2, and I'm not going into deep again for taking the closure because it's very obvious by looking at this. And I'm just ignoring the closure. Okay, sorry, because we don't have much time. And there is one tutorial video for getting the closure, how to take a closure. And this one is also there.
This last one, R plus is equal to R cube. So how it is happening, sir? I can see that R is
R determines Q, so R closure is R Q, and Q determines R, so Q closure is QR. Because
no,
we are
we can say that R cube. I'm talking about R. R can it is coming from R itself. Last.
Yeah, I said right in the initial one. Any attribute can determine by itself.
Oh, okay, sir. Got it.
Okay. And by looking at this, now what we need to do is we need to check whether the dependencies on F1 is present in F2 or not, so that we can check for F2 covers F1. So let's take this PQ and whether this is covering or not. So let's see on the closure of P, because now it has Q, so that I can write P determines Q. So this is satisfied. So take a Q R, Q determines R also, because R is also there. I will take a R closure in F1. This one doesn't have P attribute, right? So I cannot say this R determines P. This is false. So this is dependency is not satisfied. So this F2 not covers F1. Clear?
Yes, sir.
If this is also covers, F2 also covers F1, then we can say it is functionally equivalent to F1 and F2 are equivalent. Okay. So let's move to next concept of decomposition. Okay. So where the decomposition part comes is, let's assume there is a table.
Sir, is
and
the
if you want to
spelling lossless or loseless?
lossless. Why?
No, in the slide it is written looseless.
I have written currently, I guess, lossless joint decomposition.
Oh, it is looseless. Loss means double S, no?
No, single S. Oh, sorry. Maybe spelling mistake. So what we'll do is, original relation decomposed into a smaller relation in such a way that it can be reconstructed through natural joins. So if you decompose a table into smaller chunks, so that this dependencies and relation doesn't affect each other, so that it is safe to decompose in a two table, because you won't have any anomalies also. So condition for checking this lossless joint decomposition is R, R1, R2. So what we do is this R and pi. So the first condition is, if you perform a natural join, it should come to the original table, and there should be at least one common attribute. This says common attribute. It should not be equal to pi. This is common attribute. And R union R, and if you take a union, again you should come to this. And if there is only one of the common attribute, by taking a closure of that common attribute, it should determine either one of the decomposed table. This R1 and R2 is nothing but decomposed relation. Okay.
Could you please go to last slide, please?
The last one.
Yeah.
So if there is any common attribute, what you need to do is, you need to take a closure of that common attribute, and it should determine the relation R1 or R2. It's nothing but a decomposed relation. Okay.
What is the difference between the point 1 and 3?
1 and 3, it's almost same. If you take a union, that should decompose it. Maybe I should remove this third point.
No, in terms of natural join and in terms of union, I want to understand, is there any difference?
Here it won't make any difference, since the attributes are in the same.
Then can it make any difference anywhere, in any condition?
In some places it makes, if doesn't have, because union we used to do based on some attribute sometimes. Generally, I'm talking about the join, because natural join by default it's taking the common attribute, right?
Yeah, because you have written the 4 statements, so I'm not sure why these are 4 required.
Actually, I should do this. Then this is one of the example. Let's say this has a functional dependency, and this is R1, R2, and R3. These are my decomposed relations. So what I'm trying to do is I'm splitting this relation into 3, 1. So now I'm checking whether this is lossless join decomposition or lossy decomposition. If I split this, whether it's a good decomposition or not, basically. Okay. So the first condition is you take for a union or natural join. Better to take union only, right? So if you take a union of it, so this is true, right? Because if you take union A, B, B, C, C, D, and it's giving all the attributes which are present in your R. So this condition is satisfied. Natural join could be helpful if you split it into only 2 tables. So this is like maybe only 2 tables, if you say, or whenever you join some table, or you can take this natural join condition. So you can ignore this if you are not wanted to remember this. I'll tell you where it would be helpful. So by looking at this, the first condition is satisfied. And the second condition is if you want to take intersection of these R1 and R2, and the closure will be, sorry, the common attribute will be B. And what you need to do is you take the common attribute closure and to check in the functional dependency, what's the closure value? It will be B determines C. To take a closure of B, it will B determine C and C determines D. So this will be BCD.
So,
right?
As we have 3 relations, R1, R2, and R3, right? So their union should always give us R. So is it not required that
First we are checking. First we are checking with these 2 decomposition whether it is lossy or lossless. If it is lossless, then we'll move to R3.
Okay. So okay, next it is.
Okay. Now it's giving B, C, D, which is my R2 relation. It gives my R2 relation, not exactly R2, because R2 contains BC, and this closure also gives BC. So it satisfies my R2 relation, as you have seen here. This intersection 1, if you take intersection 1, it should determine either one of the relation, right? Is it clear?
Yes, sir. Yes, sir. It was either of them.
This now let's consider this is lossless. So what I will do is I will join these 2 and I will write R12, and this has one decomposition and another one R3 has another decomposition. C. Now again, if you try to union, this will give ABCD to my original relation. My first condition and satisfies again. And if there is a common attribute, it should have a common attribute, right? And the common attribute is C. If there is no common attribute, it is lossy. So we found a common attribute C, and if you take a C closure, it will give you CD, right? Here. It will give you CD.
Sir, we see R12 is ABC, right? And R2 is BC. Shouldn't that intersection be BC? Why is it only C?
Why BC?
ABC and BC when they intersect. Shouldn't the answer be?
Only one common attribute is there, right?
But the second last line is R12 intersection R2, isn't it?
It should be R3, I think.
It should be R3 in the
Yeah,
second.
yeah. R12 intersection R3. Yeah.
Oh, yeah. This is R3, sorry.
Okay, thank you.
Thank you for noting. So this will be a C common attribute. If you take a C closure, it will give you CD, and that points to R3 relation, right? So this satisfies lossless joint decomposition. Okay. Then let's come to the concept of dependency preservation. So when the relation is decomposed, so when you try to break a table into 2 or 3, your dependencies will also get.
Sir, can you give one more example of lossless decomposition?
I'll give you after this.
Okay, sir.
This dependency preservation. When a relation is decomposed, like basically when you split a table, you are not splitting only attributes like this, R1, R2, R3. Your dependencies will also be splitted, right? So we need to check whether the dependencies also get preserved, not only lossless join. This dependency should also be preserved. So that it helps to prevent anomalies and data integrity. So how can we check this? And also you have to note down, if it is lossless joint decomposition, it shouldn't be necessary so that it will have a dependency preservation or independent to each other, because basically it's independent. If it is dependency preservation, it can be lossy also, lossless also. If it is lossless, it can be dependency preserving or not also. So this thing you need to take care. And example, what we'll do is this one, functional dependency with A determines B, B determines C, and C determines D, and D determines C. Following this is a functional dependency set, and there are 3 dependencies here, which has been decomposed R1 and R2. For these R1, R2, R3, there are functional dependencies which needs to be calculated. Okay. So for this R1, you need to take a closure of A, then you can calculate this A determines B, so that you will have that. And B if you take closure of B, B determines. So based on my F1, you can take this. Similarly for F2, this one and this one. Basically, you have to take, and also you can check like this also. You can take a closure of both A, B, and you can take A, B, C, D, A. It gives everything, but in R1, it is limited to AB1, right? So I'm taking this.
Sir, how are you getting B determining A?
It's okay. If you take a closure of B plus, the B determines C here, right? And this C determines D, and this D determines C. So I can say B also determines C, right?
Okay, sir.
Similarly, you will get this and this also. So we now have this functional dependency sets for all this breakdown R1, R2, R3. And the example, now what you need to do is you just combine all those functional dependencies, whatever we computed. So if you combine, it will be like this: B to C, C to B, C to D, D to C. So A determines B and B determines A, B determines C and C determines B, and C determines D, D determines C. What I did is I just combined all three. Okay. Now you need to check this F plus equal to F or not, your original dependency. If it is not there, so from this you can see A determines B will also be there, B determines A, you don't need. B determines C will be there, C determines D. Not equals, sorry. This F plus should be a superset. Should be equivalent or superset. Okay. So, but one dependency is missing. It is D to A. So we need to check whether D to A is preserved in this F plus or not. Is it clear?
Sir, it is not circular. Above one was circular, right?
No, the steps which I am doing, is it clear? What exactly I am trying to.
Sir, can you explain after the D to A is missing?
Can you? Sorry.
Sir, line in which written D determining A is missing. After that line, can you please explain again?
I'm not getting from where I need to explain. Okay.
Sir, in page number 24.
Hmm.
In the third last line, it is written now D is determining A is missing in F plus. Can you explain from there again?
Okay, this D determines A is missing on F plus, which is not present in my original dependency, right? Because as per the rule, this should be superset, but it's missing. If it is something missing, it is not a superset. So we'll check whether this condition satisfy in my F plus or not. So what we'll do, we'll take a D plus closure on this F plus. So if you take D closure in this dependency set, what you will get is you will get a C, DC. And again, C will determine B. Again, B will determine B. So from this closure one, you can say D determines K.
So functional dependency is preserved.
So yeah.
Okay, sir.
So the dependency is preserved. If you haven't got A here, then it is not functionally dependency preserved. Right? Any other questions? That's all the week 5 concepts, basically.
Sir, we have prime attributes and non-prime attributes.
The prime attributes and non-prime attributes. Okay, I have mentioned somewhere. I don't know. We'll check.
Candidate,
Yeah. Whatever the candidate keys you are finding it, if the candidate key is A, B, C, D, all these attributes were prime attributes. A is prime attribute, B is also prime attribute, C is also prime, and D is also prime. For example, in this case, I'll just erase everything here.
all these are prime attributes, enrollment class section.
Yeah. Mm, So this is prime attribute. Here enrollment number, class, section, role, name. Class is prime attribute, section is prime attribute, role is prime attribute, enrollment number is also prime attribute. But name is not a prime attribute. It is not a prime attribute. Okay.
Sir, can you give one more example of lossless decomposition?
Lossless, okay. Do you have any questions with you, or shall I take random?
Sir, you can take random question. I don't have any.
So let's take a functional dependency, something like A determines E, E determines C, and C determines D, and AB determines again D. Okay. Let's have a relation A, B, C, D, E. So let's say this decomposition we are trying to split is A, E, and R2 is again E, and the remaining attributes B, C, D. Okay. The first condition is if you take R1 union R2, it should be R. So if you take here, the union will be A, B, C, D, right? So which is nothing but equal to R. The first condition satisfies, right?
Yes, sir.
And if you, the second condition is there should not be any null set. That is nothing but it should have one common attribute. Here the common attribute is E. And what we need to do is, third condition is, you take a closure of that common attribute, whatever it's there, common attribute closure, and that should determine either R1 or R. Now in this case, if I take a closure of E plus, this here E determines C, right? Is it determining my R1 or R2 relationship?
No, sir.
So in this case, it is lossy decomposition. If you have got A here, then it is not lossy because you got R.
Sir, we are not going to further write E. C is determining D in the closure of E.
No, right? Because you have to check with the common attribute only.
Okay, sir.
Okay, anything else? Or else we can wind up the session.
So 3NF form and BCNF is left, I think.
That will be covered in week 6.
Okay, okay. Thank you.
Okay, thank you, sir.
Okay, thank you.
Thank
you
you,
everyone
sir.
for joining.
Sir, everything will be there in fourth book.
Everything?
Fourth book which you have referred in the course introduction, that book will have all these things.
Yes.
Thank you.